Hello everyone, my name is Naveed Anwar from AIT, and today we are going to talk about one of the very important subjects which is one part in the series for building blocks for structural engineering. And over the years that I have been working, I have found that there are a couple of concepts that many engineers are either not fully aware of or they are not utilizing it to the full extent. And moment curvature curve is one of them. And the other one is understanding the modal properties. But today we will focus on this very, very interesting as well as important curve that contains a lot of information. I normally call it one of the secrets that has been kept from structural engineers. And today we will try to find what is behind the moment curvature, how is it generated, a little bit about that, but more importantly, what we can do with this curve. What are the hidden treasures behind this curve that we do not use enough? So let's go on a journey to find these treasures. Let's get into the moment curvature curve and understand how this is generated, and also look at some of the things that we can find from this curve. Let me start with this display. This is a display which maybe most people may not have seen. This actually represents the curvature capacity of a cross-section with the variation, with the axial load and various axes around the cross-section. And this is actually similar to another surface that you might be familiar with, which is the capacity interaction surface, which is a plot between axial load and two moments. They are very similar in the sense that one represents moment capacity and the other one represents curvature capacity, both plotted against axial load. And you can see that their shape is very different. And we would like to understand what the moment curvature has to do with curvature capacity and how this can be related and how we can use this information. So if you look at these two surfaces and if you look in deeper and dissect them vertically as well as horizontally. So if you look at the moment and axial load capacity, we will see that they represent a plot between moment along any axis as well as axial load, and this represents the PM interaction. And we can also see a similar interaction between axial load and maximum curvature, which represents a plot between maximum curvature along any axis and the axial load. And you can see that the picture is quite different. In one case, the moment capacity first increases with increasing load and then decreases, whereas the curvature capacity decreases as the load increases. And if we look at the plot between the two moments, then we can see kind of a circular or an elliptical plot relating moment about x and y. And if you see the curvature capacity, then it can vary a lot depending upon the level of load and depending upon the direction of the bending. So this is quite important observation from here. So the curvature capacity is very sensitive to the bending direction as well as to the axial load. Now, how did we get this curvature capacity? This actually is obtained by plotting the maximum curvature at any given point from the moment curvature curve. And that leads us to the understanding of the moment curvature curve itself that can be used to create this curvature capacity. Now, going into the moment curvature, we will see what this curve is all about and how it can be used. Curvature actually is a measure of how much something has deformed, and definitely when we bend something we can observe the curvature, and it is actually a measure of the level of bending, and it can be measured in terms of the quantities, for example the radius of curvature. So if the surface is undeformed, then the radius of curvature will be at infinity and curvature will be 0. But as the beam or the column or any member deforms, then the radius of curvature will keep reducing and the curvature will keep increasing. And this also can be indirectly measured from the strain on the cross section, because initially the cross sections, with undeformed cross section, the cross section is vertical. After deformation, it will become inclined, and that inclination will give us an indication of the curvature. So once we know how to measure curvature, we can relate it to the bending moment that causes this curvature. And then we can plot a curve which shows us the relationship between moment and curvature. And this curvature, initially, this relationship may be straight, and later we can see yielding and so on. And one of the important thing is that the slope of this curve gives us the important quantity of stiffness. And this is the first and the most important thing that we can determine for moment curvature from the moment curvature curve. You might be wondering, why do we need the moment curvature curve to calculate stiffness? Stiffness is easy to calculate because this should not be a difficult quantity. We have been doing that for a long time. However, we will see that that is not the case when the members have deformed significantly. At the initial condition, we can use the cross section, the gross cross section, to calculate the E and I and multiply them together to calculate the stiffness. And this number is good enough when the cross section is undeformed and uncracked. However, once the cross section starts to deform, then the modulus of plasticity no longer remains a constant. It changes with strain. And we also need to be aware that a reinforced cross section has two materials, steel and concrete, and we have to take the effective modulus of plasticity, not just of that of concrete. And the other problem that we can see is that when the cross section deforms, it will crack, and the gross cross section no longer valid, and the initial stiffness that we calculated will no longer be useful to us. So in that case, then we can use the moment curvature curve to calculate the stiffness. And as I mentioned, moment curvature curve is the moment curvature curve gives us the stiffness directly by taking the slope. But the question is, which slope are we going to take? Because it could be initial slope, which will give us initial stiffness, or it could be a slope of a given point at a given location with respect to origin, which will give us the secant stiffness, or it can be the slope of a given point at any given location, which will give us the tangent stiffness. And each one of them will be a different number depending upon at which point we measure the stiffness. Normally, we only use the initial stiffness in our calculations, but that is only valid for a very small deformation or very small deformation history. And beyond that, we will either need to use secant or tangent stiffness. And if you try to plot the variation of these three stiffnesses with the cross-section deformation along the moment or the curvature, you will find that they rapidly decrease. So if you have a very little curvature, as here in the beginning, the stiffness will be very high and very close to the initial stiffness or the gross stiffness. But as the curvature increases, then the stiffnesses will drop significantly, and even it can become negative, especially the tangent stiffness when the slope of the curve is negative. So you can actually get negative stiffness, which is a concept which is difficult to visualize, but it's useful in computations. The other thing that we can see from the moment curvature curve, which is also equally important, is to understand what is happening to the cross section as it deforms. So first of all, after a small application of small loading or moment, the concrete will crack and we will have a cracked cross section. And as we proceed further, the bars will start to yield, as we can see from here, and then the concrete will crush. First, the concrete, which is outside the center zone or the confined zone, as we call it, of the column or the beam, that will fail or crush, and then the concrete inside the confined zone will also crush. And finally, then we will have a residual strength when almost the entire cross section has failed, both the bars and concrete. So from this observation, we can also calculate some other important quantities which are very useful. And one of the most important one is the ductility ratio, which is a measure of how much ductility is available in the cross section with respect to the yield deformation. So we can take a ratio of the maximum curvature over the yield curvature or curvature at any point with respect to the yield curvature and calculate that ratio and then call it a ductility ratio. And this could be calculated for the failure point, or this could be calculated at the ultimate point compared to the yield point. So these ratios are very important indicators of the cross-section's status as well as its ultimate strength or its ultimate capacity to deform or ultimate capacity to resist the moment without completely giving away. Rotations and deflections are another important quantity that we can calculate, which is, as you know, is normally very difficult for reinforced concrete beams or columns because the calculation of the effective moment of inertia is quite complicated. But moment curvature curves gives us the opportunity to do these calculations rather quickly. A rotation basically is a summation of the curvature over a certain length, and deflection is in fact then the summation of the rotation over another length. So if this we use the moment curvature curve in both the cases to directly compute the rotations. We simply multiply the moment curvature curve by a certain length, and that gives us the rotation over that length. In fact, this quantity is quite useful because it helps us to compute the hinge rotations for nonlinear analysis, where we have to provide moment rotation curve rather than moment curvature curve. So we assume a certain hinge length, multiply the curvature by that hinge length, and we get the moment curvature, moment rotation values for that hinge. Deflections, we will have a separate discussion on how to calculate deflections using moment curvature curve, because I think this is a very, very powerful tool and it can be used quite effectively to compute the deflections both for simply supported continuous beams as well as for columns, slabs, and other members. Another important parameter that we can compute, or I should say estimate, from the moment curvature curve is the crack spacing as well as crack width. So basically, crack, as you know, is a summation of the strain over a certain distance. So if we assume the spacing of the crack, then we can add the tensile strain over that length, and then that will give us an estimation of the crack width. And if we assume a certain crack width, then we can determine how far such cracks will be, again based on the strain that we have determined from the moment curvature curve. And this strain is actually corresponding to a certain moment with including all of the material behavior that we have included in our calculation. So these two again are two very good parameters, although this is not exactly how the beam or column may crack, but it will give us an estimate of what roughly the crack spacing or crack width could be at that moment level, and including the effects of axial load, because moment curvature can be generated with or without axial load. So this can also be used for columns and other such members. Now, there are some other things that we can also get from the moment curvature curve, which are further insights into the behavior of the cross section, which are computed as, I would say, byproduct of the moment curvature curve calculation itself. And some programs that you use, they report these, and some don't. But we will look at the results that are reported by CSI Call, a program that I will describe in a few minutes. And so this can be used to determine several other parameters in addition to the basic parameters that I already mentioned. These include the moment curvature, of course, as we have seen already. It can also give us a relationship between concrete force and curvature. So this is a useful quantity to determine how much force is being resisted by concrete, because it is related to the stress in concrete and so on. Similarly, we can plot the steel force in compression against curvature, and this value is good because we could use this to calculate whether the bars will buckle at that point or not, and we will also have a good idea about the level of stress in compression as well as in tension in bars, and that can be used for calculating the development lengths and embedments and bar buckling and so on. Similarly, we can continue to determine strain, steel strain versus curvature relationship. We can determine the concrete strain versus curvature relationship, and interestingly, we can also find the neutral axis depth versus strain versus curvature relationship. So we can see how the neutral axis depth changes as the beam deforms. And as you can see from this graph, that it actually becomes more or less constant when the beam has lost its capacity, and it's basically relying on the rebars at the top and bottom, and concrete has primarily gone. So that gives us some idea of how many of these quantities can be computed from the same moment curvature curve calculations or relationship that we have seen. Now let me come to the tool that is used in this presentation, and this is called CSI Call. And CSI Call actually is a program developed by Computers and Structures Incorporated, CSI, in US, and I'm also part of the development team along with some of my colleagues in AIT as well as the main development team in CSI. And I'm going to describe the new version of CSI Call, which is CSI Call version 10, which is about to be released as of this date that we prepared this video. And hopefully by the time that you are watching this video, this will already be available. So let's take a quick look or brief look at this program and see how it can be used, especially related to moment curvature. The program has a lot of capability for other things, but we will only focus on what it can do related to moment curvature curve. So let's go and take a look at this program. This is the new CSI Call, as I mentioned to you, and I'm just going to create a very simple rectangular cross-section for the demo. I will create the auto confinement for now. We will talk about that in another video on how confinement and other things work. And I will go straight to the moment curvature option here. So you can see here that there are many things that you can do about the moment curvature. First one is that you can plot the moment curvature curve itself, and then it gives you, and along the curve you can see the status of the point, as I mentioned in our discussion. And you can measure these quantities, and it will also give you the basic quantities, for example, the strain, the stiffness and strain and other things in a tabular form. And you can use these quantities in your further calculation, and you can export it or copy it and do this, use these numbers for further computations. But the interesting thing that we can do from moment curvature curve here is look at the moment curvature details. So as you move your cursor on this curve, it shows you on the right hand side the state of the cross section, and you can see here that it shows you the curvature, the moment at that point, and also what has happened, that the concrete is cracked, first bar has yielded, and then here the concrete cover has crushed, and then finally the whole cross section has failed. And this information is actually quite useful because at each point we can see what really happened to the cross section. This can be done in 3D as well as in 2D. So if you watch this in 3D, you can see here at this point there are two plots of one is the surrounding concrete curve, which is here, and one is the inside, which is the confined portion. And you will see here that when we move the point here, the outside cover has already reached the capacity and has crashed and is no longer taking any more stress, whereas the confined portion continues to take the stress. So this kind of information is quite useful to understand how the confinement is working, how the cover is working, how the concrete stress block is affecting the moment curvature. You can do the same thing for the bar stress, so we can see which bars have yielded, which have not yielded here. So if you go in the beginning of the curve, you will see that actually the bars have not yielded, and then we have more or less a linear distribution of the strain and stresses, whereas close to this place here, these bars have already been gone or failed completely, and the middle bars have yielded, and the compression bars are also now not being effective anymore. So this is how the cross section has actually reached its capacity. We can also do the same thing with the concrete strain. We can see the bar strain both in 3D and 2D. So this information is actually quite useful, and we can get the information about each point here, and we can see the mesh, how it was generated. We can also get a tabular display, as I mentioned, of those quantities. And we can see moment curvature, compression, bars, concrete force curvature. I showed you all of these in the discussion earlier. So all of that can be done here. And finally, we can have the maximum curvature plot that I showed you in the beginning of the discussion. And here it is. So that is the plot between the axial force and the maximum curvature. And this is the maximum curvature at that particular load. And you can see it varies a lot along and as soon as we rotate the cross section a little bit, then we lose the curvature capacity quickly. So you can see here also, and if at this point, so we move the cursor here, we can see how the curvature plot close to higher loads, then the curvature becomes almost uniform, but at the same time quite small compared to what we can get as a beam. So as a beam, we have a lot of curvature capacity, but as a column, the curvature capacity reduces and the ductility will reduce. And that's why a lot of the building codes will limit how much axial load you can apply to a column for seismic design. So that's what we could learn from this program. There are many other options that we will look at as we discuss other topics. Okay, so we have come to the end of this interesting talk that we focused on the application of moment curvature curve, and as you can see, we have found many things that can be done by using this curve. We found the most important thing is the effective stiffness, which is so hard to compute otherwise, which includes the cracking, which includes the effect of the reinforcement, and so on. And that stiffness then can later be used to do many other interesting computations, such as compute the rotations, compute the deflections, compute the crack width, and so on. We also saw how moment curvature can give us a very good understanding of what's happening to the concrete cross section when it deforms. We saw the stress, we saw when the cover outside the confined zone starts to fail, and when the reinforcement fails and when concrete crushes. So I think this has been a very good short journey into moment curvature curve. I will be talking a lot more about the topics related to this in other talks. We will compare moment curvature with capacity surface. We will see how the moment curvature is actually generated. We will also see how we can compute deflections from the moment curvature in greater detail. So thank you so much for joining me on this journey, and hope that you will be able to contribute to the learning process. Thank you.